Okay, so the last of the gas laws is one called Dalton's law. We're actually going to do this one in the lab. Dalton's law says that gases are going to expand to fill the entire volume of their container. So they fill up to fill the entire place. They push each other out of the way and they fill in the empty spots between each other. So pressure is created when the gas particles collide with the walls of their container. So if you have a mixture of gases, so let's say you had air. Air is nitrogen and oxygen and carbon dioxide and a few other things. Each of the gases present are going to expand to fill the container. That's why air fills a room. And so the volume of the container is the volume of each gas individually. They kind of fit into the empty spots between each other. It's not like it's air. There's empty space in between each other. And so they fill in those empty spots, and they all fill up the container. It's not like the helium goes and hangs in one corner and the oxygen takes another corner. They completely all mix together and fill up the entire container together. However, the pressure that is created by each individual gas is different, okay? And it contributes to the total pressure. So if I had a container and my helium is bouncing on the walls with a pressure of 1 atmosphere, and my neon in the same container is bouncing with a pressure of 3 atmospheres on the container, then the total pressure inside would be the sum of those, 1 plus 3. The total pressure is the sum of the individual partial pressures. That's what Dalton's law says. What it looks like is the pressure total is the pressure of the first gas plus the pressure of the second gas, the pressure of the third gas, however many gases you have going along. Okay, so what is the total pressure of a mixture of gases if the partial pressures of each are as follows? Now notice, I'm giving you all of those. The pressure total is going to be all of those added together, but none of the units are the same. So 1.25 atmospheres plus, I'm going to change that 275 millimeters of mercury into atmospheres. And the 97.2 kPa, also going to change that into atmospheres. That's 101.3. And if you use parentheses, I'm sure you can probably do this on your calculator. If you don't have the parentheses, you might have to actually sit down and write them out. Let's see, make sure I put the parentheses in the right place. And I got 2.57 atmospheres. So that's not too hard. Basically, you just add them all up. So that's one of the ways it's done. Okay. So you have a mixture of gases A, B, C, and D. The total pressure is 1320. Oops. If the partial pressures are as follows, determine the partial pressure of gas C. Well, I don't have any partial pressures on here. For some reason, that didn't show up. Let's make up some numbers. Pressure of A is 200 millimeters of mercury. Pressure for B is 100 millimeters of mercury. I'm picking nice numbers. And pressure of D is 600 millimeters of mercury. Well, the total is 1320. That is the first one, 200, plus the second one, 100, plus the missing one, let's call it C, and the third one, 600. And since these are all being added, not multiplied, you have 900 plus C, subtract 900. C has a pressure of 420 millimeters of mercury. Okay, so it's just a matter of adding them all up and solving for the missing one. In this case, it was missing one of the gases. Previous problem was missing the total. It's just a matter of solving it, but keep in mind they're not being multiplied, they're added. Now, here's where you're going to do it in the lab. Frequently, gases are, the term is, collected over water. Okay, and you'll see what that means when we get into class. What it means is that the gas is bubbled through water into a container filled with water. And as the gas goes in, it pushes the water out. It displaces the water, and the gas will fill up the volume of the container. However, when it happens, When you do this, a small amount of the water actually vaporizes. It becomes a gas, a small amount, and it contributes to the pressure inside the container. Remember, okay, you have a mixture of gases. You have water and whatever the gas is that you want. You have a mixture of gases. The pressure inside the container is both of them added together. So in order to figure out the pressure of the gas, which is generally speaking what you're looking for, you take the vapor pressure of the water, the partial pressure of the water, and you subtract it out of the total pressure. So I'll show you what that looks like. So sample of hydrogen gas is collected over water. So that's the key phrase. That's what you're going to see at 30 degrees Celsius and has a total pressure of 1.032. So pressure total is 1.032, and that is the pressure of the hydrogen plus the pressure of the water. Okay. It has a volume of 240 milliliters. The vapor pressure of water is 31.8. So the first thing you want to do when you see collected over water is you want to subtract out the pressure of the water. Make sure you put it in the right units from pressure total. So the pressure of the hydrogen here is 1.032. Subtract the 31.8 divided by 760. Make sure the units are both in atmospheres. 0.990 atmospheres. Okay? And so they might ask you other questions. What's the partial pressure of the hydrogen? Well, we just solved for that. And we would say the pressure of the hydrogen is 0.990 atmospheres because we subtracted out the water. Now, here's where they tied in. How many moles of hydrogen gas were collected? Well, I have a temperature, I have a pressure, and I have a volume. So P, V, N, R, and T. My pressure is 0.990 atmospheres. I am not going to use that total pressure because I want to find moles of hydrogen. That means I need the pressure of the hydrogen alone to make it work. Volume is 0.240 liters. N is X. R is my ideal gas constant. And temperature is 30 plus 273, or 303. So putting it to the ideal gas law, doing some multiplication, and on the right side I get 24.86x, and on the left side I get 0.2376, divide, and x ends up being probably a pretty small number. Okay, because this isn't a very large volume. 240 milliliters is actually kind of small. I mean, your soda cans typically are a little bit more than that. They're about 350. So 0.00956 moles. So this is kind of a combination problem that combines Dalton's law with the ideal gas law. And you definitely will see stuff like that. But the key words are collected over water, and the very first thing you want to do is find the partial pressure of whatever the gas is all by itself.